let's cover the next section. It is quite a brief section. This is going to maybe take between 15 and 30 minutes. In particular, I would like us to look at the graphs of exponential functions. So let's share the Desmos screen and let's start putting some exponential functions up on the board, as it were. And let's see what they look like. So here are 4 exponential functions I've selected kind of at random. Let's modify this a little. We're allowed to have numbers here. Remember, a times b to the power of x. Let's do that. So, in a sense, these exponential functions all might look rather different, but really there's a lot of commonality between them. If we zoom out far enough, in fact, they become kind of visually indistinguishable. So what do all of these exponential functions have in common? Out here in the large negative region, they're extremely close to being 0. In fact, if you read off the screen, Desmos is claiming that at negative 46.16, this purple exponential function, the 1.89 times 3.65 to the power of x, is equal to 0. It isn't. That's just Desmos rounding. None of these are actually 0. They're just extremely close to 0. And they're increasing. All 4 of these functions are increasing as we read from left to right. And initially, they're increasing extremely slowly. I mean, up here, you probably literally can't see any increase. If we go far enough to the right, the increase becomes visible. And then these functions all just explode up as we start going right now that we're positive. I mean, you see extremely fast increase. This green function is increasing the slowest of the 4 functions on the screen, but by x equals 37, it's already surpassed 2,000. So this is what exponential functions look like, or at least it's one way that exponential functions can look. Let's go to the document camera and let's just roughly sketch this. What are we seeing here? Very slow initial increase, which then just accelerates and takes off very quickly. So this is one way that exponential functions can look. Now, thinking back a bit, none of the functions we've looked at have a single graph. So if you think back to linear functions, well, they're always straight lines, but they can be increasing or they can be decreasing. Or if you think back to parabolas, to quadratic functions, they always look like parabolas, but they can be open upwards or open downwards. So by analogy, you might expect that exponential functions can take on some second form, and you'd be right, they can. Let's go back to this and let's create an exponential function that looks nothing like these four. 0.7 to the power of x. And I'm not sharing this, so you can't see it. Now you can. 0.7 to the power of x is this black curve, and it's very different. Instead of this increase that we see, this extremely speedy increase, we see this extremely speedy decrease. So these curves, the first four curves, the ones that aren't this black curve, saw extremely slow increase followed by extremely fast increase. Here we're seeing extremely fast decrease followed by extremely slow decrease. So an exponential function can basically look like one of these two graphs. And sure, the details are going to vary. I mean, going back to this, the green curve is clearly distinguishable from the purple curve, but in general outline, they both look like this. So what's the distinguishing factor? What decides whether an exponential function looks like this or like this? It's the growth factor. So remember that exponential functions look like this, where this b is 1 plus the growth rate, what we have called the growth factor. And the exponential function corresponds to multiplication by B. So going back to this graph, let's declutter it a bit and get rid of all but two of these things. If we keep multiplying by 2, if we keep doubling, of course we're getting bigger. On the other hand, if we keep multiplying by 0.7, if we keep decreasing by 30%, of course, we're getting smaller. So the deciding factor is whether the growth factor is greater than 1 or less than 1. Let's try to isolate a few properties that these graphs have in common. If b is greater than 1 versus if b is less than 1, the graphs look quite different, but all exponential functions have some properties in common. For example, exponential functions have as their domain the entire real number line. They're always defined by contrast, their range is limited from 0 to infinity. So exponential functions are never negative. You see that with both of these graphs. We don't have anything under the axis where y would be negative. The y-intercept is always 0, comma, a. So going back to this, let's zoom in. Our red curve, A is 6. Our black curve, A is 1. And you see here the black curve hits the axis at 0, 1. Here the red curve hits the axis at 0, 6. The last property is going to require a bit more discussion. Exponential functions have what's called a horizontal asymptote. In the ordinary course of things, we'd already know what horizontal asymptotes are from discussing rational functions. Here, because we've had to go so much slower and we're jumping around the book, we haven't discussed horizontal asymptotes yet. So this requires a definition. Here's our curve, 1 times 0.7 to the power of x except that for the second time today, I've forgotten to share it. Here's our curve. 1 times 0.7 to the power of x. And here is a horizontal line. Y equals 0. That x-axis and all this stuff is kind of in the way of seeing what I want us to see. So I've gotten rid of the axes. Now we just have this curve and this line y equals 0. And clearly, this curve and this line are different. But the further we go to the right, the closer this curve comes to looking like this horizontal line. I mean, by the time we've reached this point, we can no longer distinguish visually between the curve and the line. I maybe go a little further. There. I just turned the curve off, but aside from maybe becoming marginally less thick, and honestly, I think that's the placebo effect. You cannot tell as I turn this curve and this line on and off, which is the curve and which is the line. They are visually indistinguishable from one another. And that is what we call a horizontal asymptote. When the curve merges into a straight line, straight horizontal line, and becomes visually indistinguishable from it. The last property is made, and both, I should finish this thought first. We have horizontal asymptotes in both of these cases. Notice, though, the behavior is different. Here we merge into the axis, the x-axis, as we go to the left. Here we merge into the x-axis as we go to the right. So we always have a horizontal asymptote at y equals 0, but the precise behavior is different. Finally, and this is maybe more of a value judgment, but it needs to be said, exponential growth is extremely fast. I mean, all the times that we see exponential growth in nature, you know, this viral outbreak 2 weeks ago, you could still believe nothing was going to happen, but the virus spread exponentially. And when it happened, when it came to America, it came to America fast. Invasive species, British colonialists brought cats to Australia. They let them loose. The cat population grew exponentially, and now Australia is just beset with feral cats. It's a major environmental crisis. If there's anything you take away from section 6.1, 6.2, this would be the good thing to remember even after you've taken the final exam and passed the course, and sort of these details fade into obscurity. This is just important to know on a kind of day-to-day basis. Credit card debt grows exponentially. It's not good to get into debt if you can help it, because once that debt is there, it just takes off.